Okay, good morning, everybody. Let's get some things going here. Okay, we're gonna work this morning on power series. You're gonna see me. Hold on. Okay, we're gonna see really why we studied some of these, various tests for convergence and divergence for series, and we're gonna see kind of things come a little bit together for us here. So, all right, yeah, we have these power series today. Okay, now let me start really by revisiting our geometric series because this is kind of what occurred for some of those examples. I'm not sure if I assigned them to you. If I didn't, there is a reason, and the reason is now. So that's kind of how I typically do some things. So now I'm going to say, okay, I didn't assign some of those because I'm going to talk about it when we get to power series. So if we start with this geometric series, something that looks like this was in that section, and they say n is 0 to infinity. So here's kind of where we're going to start. And you're going to say, wait a minute, I noticed something very different here. What's different is you're going to have now a variable x. And that's the difference. So let's start to see what the terms look like here. So we say x is 0, or I should say n is 0, n is 1, n is 2, and we're generating powers of this series, and this is an infinite series. But really, this is 1 plus x squared plus x cubed, and this goes on forever. So you had some sort of things that look like this in some of those sections that I may or may not have assigned. And yeah, there's a variable here. And the variable is x. Now, this is geometric. And you say, well, how do I know that's geometric? Well, let's demonstrate this. This is A. This is AR squared, and so on. We say, okay, if A is 1, we're going to say AR is x. But we just mentioned 1 is A, and that means R is x. So remember, we have to verify that AR squared is actually x squared. We verify this term here. And you can say, if I plug in what we know, that A is the value 1, and R is x, sure enough, we get 1 times x squared, which is, in fact, x squared. So it is geometric. Also, if some of you say, I don't have to do that, I know I can write this as, I believe this is ARN. This is the definition, or one of the definitions, right? Depends on the index. If you start with 0, you write it that way. If you start with 1, you have n minus 1 anyway. This is a geometric series. Some of you guys can see it just by looking at, oops, got to highlight, just by looking at the whole thing. You can actually find that. Anyway. I think I wanted to do this. Okay. So, of course, it's geometric. And so we have to ask ourselves again, well, since it's geometric, right, does the series converge? The series converges only if the absolute value of R, in this case, R is the variable x right here, if this is actually less than 1. So we focus on the inequality here, and we have to really determine what does that exactly mean, right? Well, the definition is really -1 less than x less than +1. And so back in the first, or I should say 12.2, you had some geometric series that involved a variable. In that section, what they would say is this particular series from 0 to infinity, x to the n, this converges for these values of x right here. So we have convergence. Okay. Well, what does this actually mean? Well, back in that section here, if you had convergence, what does it convert to? What was the sum? And you had a formula, A over 1 minus R. And so if we know we have convergence, all we have to do is plug in the values of A, and in this case, A is 1, and R is X. So this is 1, and this is X. And so our power series here of infinite terms with n is 0 to infinity, x to the n becomes 1 over 1 minus x. And that's where we're at here. Okay? And I might have to let me do it. Let me expand it for you so we get a clearer picture. 1 plus x squared plus x cubed. Well, that is equal to 1 over 1 minus x. And that's only the case for values of x between this interval. Okay? So, ladies and gentlemen, this is kind of where we're at here. And so we had a power series back in that section. They did some other kind of situations, and I might have to, I might do that here as well. But here's the idea now. Let me give you guys a definition. Definition of what we call a power series. So your book starts this off this way. Your book will say anything that looks like this. Sum n is 0 to infinity, Cn x to the n. And if we expand by looking at the index here, this becomes C0, and you say x0 plus C1, x1 plus C2, x2. This goes on forever. And that really becomes C0 plus C1x plus C2x squared, C3x cubed, goes on forever. Here's your power series. And of course, you have here C0, C1, C2, C3. In other words, your CIs for all I are called constants. And your x is a variable. So here's your definition of a power series. Also, here's the big question. Here's what we want to be concerned with. Right? For what values of x do we get convergence? So we want to know, when does a particular power series that looks like this, do we get convergence? Okay, and of course, when you get convergence, the infinite sum is going to be a function. So this portion here, they're going to call f of x. Now let me clean it up and say to you, when you have that convergence, they're going to call that the value of the function, really. That's your f of x. And I guess we can do this. Okay, here's the f of x. And so it kind of looks like, in summary, we can say this infinite sum of Cn xn will be equal to that function. We're going to call it that function. And we're going to give you another definition. The domain of the function is the set of all values x for which we have convergence. All right, so whatever value of x here, every input, we need the series to converge. This is what they're talking about. So this is the domain of the function. Set of all values for which we have convergence for the power series. And we can say series for short. Okay, so this is kind of the definition of what you're looking at. And that's going to give you really three kinds of answers, by the way. So here's what we're going to see. I'm going to say to you, here's a fact. Power series converge in three different ways. Here's what I'm going to say. They're going to converge. The first is at a point, meaning one value. The second is in an interval. And the third is over all real numbers. What I'm really describing here is the domain of the function f. So you're going to have three types of domains that we're going to see, and we're going to formally write it down. It's going to have convergence at a point, convergence in an interval, or it's going to converge for every real number x. And that's really going to be the domain of the power series because we define it that way, right? Here's the definition. N is 0 to infinity, Cn x to the n. This is what we're describing. I'm also going to give you another definition of a power series. This is a power series that is centered at the value x is a. So you can see, I guess we're going to keep it in definitions here. N is 0 to infinity, Cn x minus a to the n, which really, when you start plugging in the values, you get C0 plus C1 x minus a, C2 x minus a squared, plus C3 x minus a cubed, and that goes on forever. So the center, we say, of this power series is A, and you have it right here. We could have said this prior definition, the center was 0, because you can replace this with an x minus 0. We don't, but it's thought of that way, right? X minus 0 is just x here. So that could be centered at 0. You can say that. And this here is centered at A. And again, it's the same kind of question. For what values of x do we have convergence? And when we do, that's equal to our function. And we can say now, what kind of domain situations will we have? Well, the same thing. Either convergence at a point, in an interval, or over all real numbers. So we'll give you some kind of definitions here and show you how to really go about it. And I'm really going to start with, of course, I'm going to give you some examples. But we're going to start with, the book does have a good example, and I guess that's a good place to start. But I think even in my notes, I start with that one. But we can give you guys another. Of course, we will. I try to get away, as you guys know, from examples in the book. Try to come up with a good example. But I have a lot of different ones we could look at. So I think we just want to get started here and show you the idea. So we have a power series. And if you really look at the terms here of the series, where n is 0, we have 0 factorial x to the 0, plus 1 factorial x to the first, plus 2 factorial x squared. That goes on forever. So 0 factorial, though, if we look at those details, that's 0, and that's 1. And 1 factorial is 1. 2 factorial is 2. So you're seeing here 1 plus x plus 2x squared plus 3 factorial is 6. That's 6x cubed. 4 factorial is 24. 24x to the fourth. This goes on forever. So we want to know, for what x do we get convergence? Okay, now here is why your past matters, meaning what we did in the past with our various series tests matters a lot. You're going to have to use, to find this interval of convergence, right? And we call that the interval of convergence. I'll formally write the definitions. But in order to find the values of x for which you get convergence, you're going to have to use an appropriate test. And you might say, what test do I use? Well, I'm going to use here. So I'm going to say you're going to use an appropriate test. And in this case, you're going to use the ratio test or the root test, really, in all honesty. So, because I don't have an nth root, and you say, well, yes, you do. You have an nth root here. Use the root test, like we said yesterday, right? So hopefully you guys are reviewing these things as we go along, right? Like we said yesterday, you need an nth power everywhere in the terms, whether it's a product or whether it's a fraction. You don't have it. You have n factorial here. So you don't use the root test, ladies and gentlemen. You have a problem. So in this case, the appropriate test is going to be the ratio test. You're not going to use that root test. And by the ratio test, that means an is n factorial x to the n, right? So if you guys remember, I did a whole bunch of examples of the ratio test, and that's why you study it. So for the ratio test, we need the next term, the next future term, which is an plus 1, which will be n plus 1 factorial x to the n plus 1. So the absolute value now of that ratio is n plus 1 factorial x to the n plus 1 over n factorial x to the n. And you're going to use your properties of absolute value again. I wonder what my blood sugar level is when this happens. I think I'll just do this. Let's keep it straight. All right. Okay. Well, let's use our properties. But I guess before we use properties, let's actually simplify, right? We're going to look at each term. That's n plus 1 factorial. So if you remember, we write this as n plus 1 times n factorial because we're going to cancel out with this n factorial down there, right? And then we look at these properties of exponents, and that's going to be x to the n times x to the first power, and that's simply over that n factorial x to the n. So we're going to cancel some things out. N factorial is going away. Okay. X to the n's going away. And then you say, hey, I have here this equal to n plus 1 times x. And by saying here the following, using the product rule for absolute value, you're going to end up with, let's remember, we're dealing with natural numbers, so this portion is positive. So we have n plus 1 times the absolute value of x. Okay, now here's what you always do at this point. When you get down to the absolute value of x, because x could be positive, it could be negative. So I don't get rid of the absolute value. What you focus on here is this n plus 1. Okay, so we're going to assume, since we don't know, you're going to always assume here the absolute value of x is not 0. And you're going to see why that is an important step. So assuming this thing is not 0, when we take the limit now, let me try to get some space here. When you take that limit, as n goes to infinity, for the ratio test, this is really taking the limit of n plus 1 absolute value of x. Now, you're thinking of, for limit's sake, since this is about n, it's not about x, n goes to infinity, you're going to pull out this x as if it were a constant because it doesn't apply to the variable. So you get absolute value of x times that limit, n goes to infinity, n plus 1. Now you know that this limit here is infinity. And so you might say, okay, well, what does this mean? Well, it means the whole limit, irregardless of the absolute value, right? Because this is going to be a positive number. The absolute value is x could be positive, x could be negative, but in absolute value, it's positive. So that this limit, the product there is simply going to be, again, infinity. And by the ratio test, that means the series, we have divergence. So, okay, you have divergence, yes. But for what values? For all real numbers x, with the exception of what you see here. Okay, so here's kind of an idea of how this works. We have to now consider, what about the absolute value of x being 0? Well, then that means that x is 0. And what this really means, if x is 0, ladies and gentlemen, if I go back here and I place 0 here wherever there's an x, this is the only time we get convergence, when x is 0. Because the sum here will be just equal to 1. So I just want to look at that detail there and show you guys. So here's how you answer the question here, right? Here's what this means. And I'm going to put the factor in black. We have convergence when x equals 0. And if I put this in terms of a set, if I list the solution here, x is 0, this is what we call convergence at a point, a single value. So there we are. Like I promised you, it's going to converge either at a, where do we write it down? I'm looking for it. It's going to converge either at a point, in some interval, we'll see what that looks like, or for all real numbers. Okay. 0 factorial x to the 0 is, oh, is it 1? Oh, let me maybe made a mistake. Let's double check. Is that first term? Let's look at that. Maybe going through this. Oh, sorry about that. That's 1. I apologize. I wrote it down correctly, but I didn't write it. This portion here is. Let's go back. Let me find the eraser. 0 factorial, ladies and gentlemen, is 1. and then 1 times 1 is 1. And so this is that first term. So we are okay. All right, thank you for that small correction, if that's what you mean. However, yeah, it's 1 times 1. We got that. Thank you so much. If your question is why is 0 factorial 1, this is actually goes beyond the scope of our course. But anyway, I could talk a little bit about that, but it's interesting. The factorial is really a subset of a bigger function. I believe it's called the gamma function, and I'll have to look that up. But it comes from the gamma function. And gamma function applies for, I think, all real numbers or an interval of real numbers. And factorial, it reduces to factorial for natural numbers or whole numbers. That's a short cocktail party language version of it. But, all right, thank you, Winmore. Yeah, thank you for that. I've, like I say, I'm not drinking coffee and because of blood sugar issues, and I'm sticking to green tea, and it takes a little longer, for me to get going. All right, here we go. You got convergence only at a point. Okay, good. And I want to show convergence here, probably for all real numbers now. So I'm going to get another series for us, if I can find one that gets convergence. Let's try this one here. Good. I'm going to try this one. I'm not sure if it's an example in your book, though. Sometimes it's unavoidable because they take some very simple illustrations here, which are sometimes good, but I try to stay away from them. You guys already know that. So I'm not sure if this is in your book, but okay, can we start with 0? I guess it doesn't matter if we start with 0, but yeah, I don't know. I have here in my notes 1, but that wouldn't matter. So if we said, what do the terms kind of look like here, right? If I started with 1, square root of 1 x plus square root of 2 x squared, square root of 3 x cubed, and so on. That's simply x plus the square root of 2x squared plus the square root of 3 x cubed, and so on. Okay. Again, we want to know for what values of x do we have convergence. We use an appropriate test. Even though I have x to the n, you're not going to use the root test because here you have the square root of n. You need an nth power for that term as well. So we're going to use, again, the ratio test. So we have an. An is square root of n x to the n. An plus 1 is square root n plus 1 x to the n plus 1. So when we look at the ratio in absolute value, we get square root n plus 1 x to the n plus 1 over square root of n x to the n. Square root n plus 1 x to the n times x over square root of n x to the n. And so when we do our algebra, meaning we cancel here, what we're left with is the square root of n plus 1. I'm going to actually put this under a single radical times x. And by product rule, we have two different terms. Let's separate those. I guess I'll put it down here. Okay. Now, this portion here, we can say the answer is positive, so we can get rid of the absolute value. Then you have the absolute value of x. Well, anyway, okay. And so again, let's assume this term is not zero, because do you guys understand something important here? If you allowed this assumption, because what you're probably going to have is that if the absolute value of x equals 0, let me say this to you so that we get that out of the way. If this portion equals 0, well then 0 times anything equals 0, and by the ratio test, that 0 is smaller than 1. So what you just showed is simply that it converges for only the x value being 0, because that's the only way you can get the absolute value equal to 0, is when x is 0. So when x is 0, the absolute value is 0. The product of these two terms now is 0, and that's smaller than 1. We got convergence. So we're going to assume that the absolute value of x is not 0, because we already know that if it were 0, we get convergence. It's kind of a trivial thing. So you always guarantee that you have convergence in a very trivial way at 0. And if you get back to the 3 criteria, okay, that I'm showing you, you're always going to get at least this, meaning convergence at a point which is 0. And that's just kind of a trivial solution here, meaning it's going to happen for everything. So that's why we say assume that this is not 0. And then, because we know we have the trivial solution, and so when we take the limit now with that assumption, we can get a very clear idea of convergence for really the other values other than 0. And like I said before, this is pulling out, since our limit here is about n, not about x, we can think of this as a constant only in the sense that we pull it out of our limit question. And now by the algebra here, what's under the radical, ladies and gentlemen, is n over n plus 1 over n, which is 1 plus 1 over n. So I can replace this portion here with that. Or we can say the following. We have the absolute value of x times the limit as n gets big, square root 1 plus 1 over n. Now this limit is going to equal the square root of 1, which is going to be 1. Right? So this portion goes to 1. The square root of 1 is 1. Anything times 1 is itself. So this equals the absolute value of x. We took the limit. And what do you have to have in order to have convergence? That this has to be smaller than 1 in order for the series to converge. So for convergence, your absolute value of x is smaller than 1, and by definition, -1 to 1 is what we're going to start to call, this is an interval, ladies and gentlemen. So you have an interval of convergence. And you say, oh, okay, good. So here's where we're going to start to look at this, these convergence and intervals of convergence. However, and let me go back. I'm going to just say this because I'm going to formalize it and tie it together. You have an interval of convergence now. Like I said, here's a fact. Now we got that interval of convergence. But if you really want to know about an interval, and this is really what's going on, we can write this in interval notation. This is -1 to 1. However, I'm going to note a few things for you. Intervals in this context look like this from A to B, where they're both what we call open intervals here at the endpoints. This means include A, because you have a bracket. This means include B, because there's a bracket. This means include both endpoints, because there's brackets. So when we're talking about intervals of convergence, your answers are going to be either one of these intervals. And you say, why? Well, I mean, you know by the ratio test, because it's a strict inequality, right? That's going to give you this, both endpoints, it's an open interval. But what's new here for you, what you're going to have to do is we have to check the endpoints. So I'm going to write that down. We need to check the endpoint values. In other words, we've got to check when x is -1, and we check when x is +1. So you're checking these endpoints. Okay, so let's go back and clean this up a bit. We're going to check that endpoint. That's what we mean by x is -1. We're going to check this endpoint. That's what we mean by x is 1. We have to find, do we have convergence or divergence? So you check that by going back to the original series here. There's the original series. So if I plug in the value, let me write it down here. The original series looks like this. Sum square root of n, x to the n, where n was 1 to infinity, we're going to have to check. X has to be -1. And if we say, okay, what happens then? Well, we get this series here. 1 to infinity, square root of n, -1 to the n. This is alternating. Okay? Because we have an alternating mechanism, right? This is the mechanism. And now this is why the other tests come in, why you study the other tests. So you might say, well, what did we study? Well, we studied ratio. Well, we got ratio test, root test, the integral test, the alternating series test. We got the test for divergence, a big hint, test for divergence. So if I said, can I look at this way? Because I can't use the alternating series test, because this term right here, the square root of n, is actually increasing. It's not decreasing. So I can't use the alternating series test. Alternating series test applies when that term is decreasing, but that's a big hint. If it's increasing, well, as n gets big, this is going to go to plus or minus infinity because it's increasing, this radical. And you might say, well, why is it plus or minus? Because the alternating mechanism. And then if it goes to two places, the limit does not exist. So what that means is this series will diverge, or we say diverges by the test for divergence test. And that happens when x is -1. And then you say to me, okay, well, what about the other one? You have to check when x is +1 as well. And I'll say, okay, when x is +1, you plug in +1 now for x. So you get the square root of n, You get 1 to the n, which is just 1. So the series now, when I plug in 1 here, go back to the original. Plug in 1 for x. We just end up here with the square root of n. Now again, what do I notice about this? I have to show convergence or divergence for this series because we're looking at now when x is positive 1 at the endpoints. So when I plug that in, or when I look at that series, the first thing I remember or see is this is a series of increasing terms, right? Square root of n is an increasing sequence, and that increases forever. So I suspect if I say, what's the limit of the square root of n as n gets big? Well, that's infinity. And you say, what does that mean? Well, that means it diverges by the test for divergence. So that divergence test, ladies and gentlemen, is a very, very test for divergence. It's a very, very important test. It's something you want to know. It shows up here in these kind of questions. So for both of these values, we had to check. -1, +1. For both of those values, we check the endpoints, and we find that we do not have convergence. We have divergence. Because if you said, hey, the ratio test, Mr. Judge, when you went back here, remember, the ratio test, if the absolute value is equal to 1 by the ratio test, it's inconclusive. Well, when x is -1 and +1, that's an absolute value 1, we just check the endpoints for convergence. So in summary, the interval of convergence for this solution is strictly going to be -1 to +1. It's going to look like that, which by definition is this kind of interval, so you guys know. So that's every detail. You're going to have to check the endpoints because in some cases, you might have both endpoint values offer convergence because remember, when the ratio test equals 1, like I said, it was inconclusive. That means you don't know. So we do have to check those particular endpoints. And, you know, that's kind of what you're working with. Anyway, I thought that was going to give us a different kind of answer. Let's try to check this series here. It's a very important series. Another example. Zero to infinity, and x to the n over n factorial. Another power series. If we look at the terms, we get x to the 0 over 0 factorial, x to the first over first factorial, x squared over 2 factorial, and that goes on forever. So we get 1 plus x squared over 2 plus x cubed over 6 plus x to the fourth over 24, and that goes on forever. Okay, so parentheses or brackets? Parentheses. Parentheses. There you go. Good. Okay. So in this next example, we want to look at the values of x for which we have convergence. And again, as you guys can probably see, the ratio test. So an will be x to the n over that n plus n factorial. The next term is x to the n plus 1 over n plus 1 factorial. And we have the limit here, an plus 1 over an. And you know, we're going to look at it this way first. We're just going to look at the absolute value, and then we'll put the limit. And so remember, an plus 1, x to the n plus 1 over n plus 1 factorial. And now I'm going to multiply by the reciprocal, which is the same as dividing, because that saves us some time and energy. And use some algebra here, right? Algebra here, and write down that definition, or rewrite the definition. X to the n times x, n plus 1 times n factorial, because I'm going to cancel some terms. So now you say, okay, n factorials are gone, x to the n, x to the n, and we say, okay, what do we have left? Absolute value of x over n plus 1, which is the absolute value of x over the absolute value of n plus 1, absolute value of x over really n plus 1. So we're going to find the limit now as n gets big of the ratio, which is the limit, absolute value of x over n plus 1. And again, you pull out the absolute value of x. So you're looking at the limit here. Now you know if x is 0 in absolute value, we get convergence. It'll be trivial. So we assume the absolute value of x is not 0. So absolute value of x times that limit now, ladies and gentlemen, this limit goes to 0. And again, we have a non-zero number times 0. Well, that equals 0. And this is going to be less than 1. Now, this happens for all x. I'm going to emphasize this. This happens for every x value. Now you say, how do I know every x value? Well, they said assume x is not 0. Because we know, or I'm sorry, let's take it back. The absolute value of x is not 0. What that means is x can be any number but 0. So it's positive numbers and negative numbers. This is what the assumption is really saying. X is 0 or x is less than 0. Because the only time you get the absolute value equal to 0 is when x is 0. So you might say, but Mr. Judge, why are you saying all x for this example? Well, we're saying all x because we know when the absolute value of x over here, let's write it down again. When that's 0, that implies that x is 0. We get the trivial solution. But if you assume it's not, which means x is positive or x is negative, and you still get this limit equal to 0, which is smaller than 1, this means by the ratio test you have convergence. And convergence for what? Well, convergence for when x is 0, positive, negative, which means all real numbers. So here is an example of where you say any real number will make this particular series converge. Okay, so this converges for all real numbers x. I'm going to erase this. I'm going to say this is here finite for all x, meaning all real numbers. And how you write that as an interval is what you see here. So here's the last kind of example, I should say, of what you can see. You can see that interval of convergence be every real number. And we're going to go back to this statement because you do want to show people, again, these kind of things where you say, guess what? You're going to have either convergence at a point, convergence in an interval. We already discussed what kind of intervals that meant. Or you're going to have all real numbers. And that's going to be the domain of your function. The values of x really for which you have convergence. So for today, you're just kind of really worrying about the intervals of convergence. Now you might say, you're using that phrase interval of convergence. Can we formalize that in any real way? And I will. I'll give you the formal kind of description of what your book does and how your book describes it. I went through kind of how the work goes about in terms of these power series, how you answer the questions, how you go about it. But let me formalize and tie that in. Let's see how your book describes your kinds of solutions here. Yeah, your book will give you this theorem here. The book gives it to you as a theorem, but it gives it to you very general. Here's the theorem. For the power series, and it gives you this more general way, and you say, why is that general? Well, A can be 0 here, ladies and gentlemen. That can be 0. So it's going to give you what we call a very general representation of a power series here, okay? So you have a power series. So for any power series, we have 3 possible answers. One, the series converges at x is a. Now, if a is 0, you see it converge to 0, like the prior examples. The series converges for all real numbers. Number 3. And here's what I'm getting at for the interval answers. Here's how they describe this. There is a positive number r. That's a different r. It's really going to be what's called the radius of convergence r, such that the series converges. Let's make sure we spell that correctly. If the absolute value of a minus x minus a here is less than r. And I'm going to say, we're going to note, it's going to divert. That means it diverges outside of this. And so if I take a closer look at what this means, I'm going to have you guys note this. The absolute value of x minus a being less than r, by definition, this is equivalent to minus r less than x minus a less than r. And if I add a to the middle, the right, and the left, we have here a minus r less than x less than a plus r. And that's how your general answers look in terms of what we call the interval. They look like this. But you do have to check the endpoints. That means a minus r and a plus r. So you have to check that to make sure you get the right answers. And, you know, your book says, okay, you're going to get something that looks like this. A minus r, a plus r, or you can get, if you turn that into a bracket, that means it equals a minus r, a plus r, and 2 brackets. So this is the possible answers here. R over here is called a radius of convergence Okay, and so you can have R being different values. R can be 0, or R can be even infinity. So you have this radius of convergences. Or R could be any positive number, right? So we talked about that, and so yeah, we give you every kind of detail of what you actually have here. So let's see if we have some time. I'm going to try one more here. I'm going to give you guys a good example. Let's give you something that looks like this. Maybe, let's see. How about x minus 2 to the nth power over n? And we'll say n is 1 to infinity. So if you start to look at some of these terms just by expansion, you get x minus 2 over 1 plus x minus 2 squared over 2, and that goes on forever, which is just x minus 2 plus x minus 2 squared over 2 plus x minus 2 cubed over 3, and then that goes on forever. Okay, we're going to use the ratio test. An is x minus 2 to the nth power over n, an plus 1, x minus 2 to the nth power over, next term, add 1, absolute value of the ratio. X minus 2, n plus 1 over n plus 1 times multiplied by the reciprocal. So your algebra is going to be right here. You cancel. And that looks like that's the only thing that cancels. This is left, this is left, this is left. Now, as you go through many examples of these, you might say, Mr. Judge, do I really have to do every detail, or can I go straight to the fact that I have n over n plus 1 times the absolute value of x minus 2? And I'll say, you can do this. This is fine. Okay, n over n plus 1, absolute value of x minus 2. Now, here, though, you will assume the absolute value of x minus 2 is not 0, because we're going to look at the limit, right? So you look at the limit now of that ratio. And you're pulling out that x minus 2, because this is a limit that involves the variable n. So there you go. So this is what we're saying. We assume this portion here is not 0, right? You're assuming it's not 0, because if it were, that makes your answer trivial, because 0 times anything is 0 there, really. And even if you had 0 times infinity, you'll have an issue. But anyway, okay. So divide every term by the highest power in the denominator. And you see this is the absolute value of x minus 2. And that's going to be times 1. Because you say, why 1? Well, this portion is a limit of 1 over 1 plus 1 over n as n gets big. And this goes to 1. So that's times 1. Right? Isn't that equal to 1? So you get the absolute value of x minus 2. Now, in order to have convergence, this has to be less than 1. And then you have convergence. So, in some real sense here, this is your radius of convergence here, right? R is 1 because you're using the definition that x minus a is less than r. So you only have convergence for these values here. You have divergence for the values greater than 1. At the endpoints, we just don't know. It's inconclusive, right? Because we know here, greater than 1, you have divergence. Equal to 1, inconclusive. Okay. So we have to take a look at what that interval really is. Absolute value of x minus 2 is less than 1, is negative 1, less than x minus 2, less than positive 1. The middle, the right, and the left. 1, less than x minus 2, less than 3. Add your 2's. 3, less than x, less than 5. So, ladies and gentlemen, this is guaranteed to be convergent by the ratio test, by what we set up here. Okay, outside of these values, we get divergence. So remember, we have to let x is 3, we have to let x is 5, because we have to check. We have to check the endpoints. Now, the original series here is, which one was this? This is x minus 2 to the n over n is 1 to infinity. That's your original series. So let's check. You say you have to check when x is 3. Plug in 3 for x. If you plug in 3, 3 minus 2 is 1. You get 1 to the n to the over n. This is when x equals 3. And this portion here is really 1. So you actually have the very famous harmonic series, right? So this is the harmonic series. And that is the very famous divergent harmonic series. So when x is 3, we have divergence. Okay? All right. We have a question here. We add plus 2 twice. Not sure what that means. What you have here is these inequalities here. You add 2 to the left, 2 to the middle, 2 to the right to get x by itself here. And so you get 3 less than x less than 5. Not sure if that's the question. Check when x is 5 now. You're going to plug in for the series now 5. You go, okay, what do we get here? We plug in 5 here. We get 5 minus 2, which gives us 3 to the n over n. So double check here. Let's see if everything's okay. X minus 2. Okay. So it looks like we're okay. When we plug in 3 minus 2. Yeah. So, Oh, I'm sorry. Oh, thank you, Kirby. Thank you for adding that. Catching that. Okay. All right, let's double check. Over here is the reference. Ooh. So I'm looking at something and go, something's not right. I know the answers already. Okay. Good job. No, Kirby's correct. Okay. Good job. Okay. So we check here. No, you're correct, Kirby. We don't add 2 twice. We add it once. Good job. We got 1 and we got 3. Okay. So you have to let x be 1 and x be 3, and you check. We already checked here when x was 3. Good job. Okay. So I thought, wait a minute, something's very wrong with this answer here. All right. Now we have to check when x is 1. So you say let x be 1. So when I plug in 1 for x now, not 5. Let's make that red. 1 minus 2 is negative 1. There we go. Now it's correct. So we know this is the very famous alternating harmonic series. Now the alternating harmonic series converges, right? And it converges, if you guys remember, by the alternating series test. So we check the endpoints when x is 1 and when x is 3. We only get convergence when x is 1, not when x is 3. So you say, what does that mean about our solution? You have to include when x is 1. So the actual interval of convergence includes the endpoint of 1. And written in interval notation, that's 1 to 3. So yes, ladies and gentlemen, this is exactly what you need to do for these power series questions. And, you go through a bunch of them using ratio and root test. You will see what I'm talking about. And so today's Thursday. And so what I'm going to say to you guys for homework on this particular section, this is 12.8. You guys can do, 3 to 28. I typically say all, but I say odd, but I would try them all. What I'm going to do for you guys is I'm going to focus on, I can say odd here. Okay, for your homework. And 3 to 28 odd, I'm going to say try those for homework. I will post online since it's Thursday. I want to make sure I get you guys by this weekend, hopefully tonight, tomorrow, at least by tomorrow, you'll have additional examples on power series, looking at these intervals of convergence. So I'll give you guys additional examples. So make sure, and I know you subscribe. So since you subscribe, you'll get the notification as soon as it goes on YouTube. But I'll also link it to my website and link it to Canvas, so you guys get the announcement there too. Now, we have a good question. When is our test for? Let's go back to the browser. I would like it, but I'm not going to change it. I have my reservations about all this, but it's actually, if we get this to work, on our schedule, we'll talk about that. It's June 1st. I would like it to be May 25th, but I can't change it because all the lawyers in the room might freak out. So, I would like it to be that day. And then you have your final on June 2nd. So, yeah, we'll see what we can do. All right. I'm going to see some stuff that we can do. But so far, it's scheduled June 1st. We can't change that date. There's been so many changes already. So you guys have some predictability here. And, of course, it's going to be on sequence and series for that test 4. And, yeah, so you have essentially a sequence and series test, and I think a little bit of that polar calculus. Yeah, polar calculus and sequence and series, and of course I'll give you guys a study guide. I think I'll work on some things and ideas this weekend aside from your power series examples about how we're going to proceed here with the rest of the course. And then it looks like you have your final the next day, which is like yikes. But anyway, I have a few ideas for you guys, so stay tuned. So far, what I'll say is make sure you study the chapter 12 material on sequence and series. And, come Tuesday or even over the weekend, I might send out a correspondence to you guys over that. So definitely think of your June 1st test 4 over sequence and series, chapter 12 with a little bit of polar. And then we'll talk about what we have to do for that final, I guess. But anyway, if you have any other questions, concerns, or issues, thank you guys for all your help. It's very helpful, and it's very encouraging to see that you guys are awake, because I'm barely awake, but that's only because of age and, sugar level maybe. Okay, because high blood sugar actually, puts you in a coma. it puts you to sleep, believe it or not. So I can tell when my blood sugar is high. I'm trying to look at my writing and see where that's relation to that blood sugar. But anyway, you guys don't need to know these details. Check this weekend. I'm going to put up this Power Series examples for you guys. You'll have it on your final. You'll have it on your next test. I'm trying to put a lot of extra examples for you guys. And then we'll be good to go for the other courses. Like these things are studied in differential equations. And you'll see what I'm talking about. Okay? So take it easy. We'll see you guys when we see you. I hope I clarified a few things. But if there's any more questions, just contact me in office hours. And you guys have the announcement I sent early this week. I just merged the two classes together. So take care. I'll see you guys later.